My name is Sahil Trivedi, and this is my Physics 2211 Lab Report 4, where we're discussing harmonic motion. So getting right into it, the table of contents has the introduction, relevant physics principles, the experimental data analysis, computational data analysis, results and discussion, and then lastly, the conclusion, where we'll discuss the two data types and compare their solutions. So looking at the introduction, the purpose of this experiment is to allow us to examine a spring mass system which can help us gain insight into the motion of oscillation and how to much better predict it. Assumptions include extraneous variables like friction and air resistance will be unaccounted for, and they'll instead be included as dissipative forces in the physical demonstration, and they'll be completely ignored in the computational model. As for the main results, the conservation of energy is still largely observed, and loss or dissipative forces like friction and air resistance are seen as differences in the experimental data as compared to the computational model. Looking at the fundamental physics principles, we obviously have the velocity update and position update formulas on the left, which many stuff is derived from. We have the gravitational force formula, which will be utilized to observe the conservation of energy. And then at the top formulas, you have many, including the F equals ma, gravitational potential near Earth, as well as spring potential energy for the oscillation. Looking at the experimental data, we decided to select the video demonstration, which you can see here, and here it is in the tracker app where the data is being collected. Now, moving forward, you can see that as for the experimental data, conditions, and observations, the system was considered to be the spring, mass, and Earth, so that no external work should be considered on the system. As for the initial conditions, we left our mass as 0.402 kilograms. Our initial position was negative 90.63, 19.33, and 0 meters. This might seem a little bit misleading, but it's basically because there was no scale in the actual demonstration, but even scaled up units are just scaled by a factor, so the data should be perfect. Our initial velocity was considered to be 0, as it's the time it was released. Our spring constant was 0.683 newton meters, and our L naught, like resting state, was 0.123 meters. Looking at the computational model code, you can see that much of this stuff was hard-coded in. So you could have the ball mass at the top, which is 0.402, then the ball position and ball velocity, which was all hard-coded in. And then you have your constants like G, your spring constant, and your relaxed length of the spring, which were coded in. And then at the very bottom, you can see how our kind of derived variables were decided. So you can see that L was the ball position minus spring position, our L hat was L divided by the magnitude of L, and our S was the difference between the magnitude of L and the original L naught. And at the very bottom, you can even see the forces, including the kinetic energy, spring potential energy, and the gravitational potential energy. Moving forward, you can see the rest of the computational model code where T was kept less than 9.43, so it matched our physical demonstration time. The initial energies are all defined there. The F gravity was coded in as the negative ball times mass times gravity. The spring constant, the force of the spring is the general spring equation of Ks L hat. The F net was F gravity plus F spring, and then the ball velocity and ball position update formulas were coded in, and below that again is our L hat, and S values. And then at the very bottom, you can see the entire kind of range of energies that were decided on, including K, and then delta K for the iteration, UG, delta UG, spring potential energy, and the final energy of the entire system, which we expect to be conserved. Looking at the results and analysis, on the left side, you could see the model and experiment for the X position versus time, and on the right, you can see the model and experiment, the Y position versus time. You could see that the oscillations don't align perfectly, and there is a lot of discrepancies in the X position versus time, and even some in the Y position versus time. This is likely attributable to the dissipative force, which we'll discuss later. So a possible source of error was improper tracking. Since it was subject due to human error, it was done by hand in the tracker app. Number 2 is other forces are always acting on the system, which are the dissipative forces, and cannot be accounted for perfectly. So there could be some extraneous force even besides just the traditional dissipative forces that we didn't account for. As for discussion 1, conservation of energy is in fact proven to be correct as seen by the computational model, Anticipated forces is the reason that we saw some level of differences between the physical demonstration and computational model. As for discussion 2, the spring constants can be slightly different depending on the direction of motion. So if you were to pull a spring in the x direction and pull a spring in the y direction, due to imperfections, the spring constant could be different, and this results in a different oscillation period. Thank you for watching. That was my physics lab report 4.